Hi, I'm Huiba. I'm a senior staff engineer working at Alibaba Cloud Storage. Before Alibaba, I once worked in Meituan, which is an internet company with the third highest market value in China. I was in charge of a distributed block store there. I once worked in IBM China Research Lab in a team for Mambo, which is a simulator of power architecture. I realized the shadow page table for Mambo to greatly improve its performance for load and store instructions. I also have some publications in recent years. Today, I'm going to talk about DADI, which is an abbreviation of data acceleration for disaggregated infrastructure. And container image is a major use case. In cloud computing, we often take data centers as a computer. So we believe there's the need for a novel layer of system software that plays the traditional role of caching in a computer. And the layer actually can do more than caching, so we call it acceleration layer. And in this talk, I will describe how we apply DADI to container deployment at scale. But why we need DADI in Alibaba? Alibaba is the biggest e-commerce market in China. It is consists of a large amount of microservices, and all of them are heavily loaded during shopping festivals. And we have multiple such events in a year. It is very difficult for us to precisely predict the resource demand of every service. Over-provisioning of all the services is too costly. There will always be unexpected high demands for certain services. So emergent extension is a must for the system, and elasticity is critical to the success of Alibaba. I believe many internet services are also facing the similar problem. So what exactly is the problem? It is that container deployment is slow. Tail latencies may reach tens of minutes. And the problem is even worse for large-scale deployment, or those with large images. The total cost is proportional to image size multiplied by the number of containers to deploy. The process involves downloading, unpacking, and the decompression of the whole image. But the fact is, only a small portion of the image is actually used for the starting of application. Some research revealed that the portion is even smaller than 10% on average. And the process is not only slow, but also a big noise that affects container already running on the same host. So the reality is far from the promise of elasticity of cloud computing. And elasticity is a key value of cloud computing that should be strengthened rather than weakened. There is already some work on this problem. The first is P2P downloading, which is widely used in large container clusters. It significantly improves downloading speed in those environments. But the result is still far from satisfactory, as it solves only the server side of the problem. The actions of downloading, unpacking are still there in the client side. And there is a huge pressure for block storage of cloud platforms, and thus bounded by the latter. Slimming the images is another attempt to improve the deployment performance. But this approach is not universal because it is hard to automatically find all the dependencies for every application, and it becomes hard to support ad hoc operations within containers. So we believe the ideal approach is a remote image that avoid the beforehand downloading and unpacking. And we need P2P transport for large clusters to cope with the scalability problem. But the problem is container image is not viable for remoting, as it is not seekable. The format was designed for sequential unpacking, so it is a must to change the format. And I believe it is better to design a new one rather than confining the current one. There are two choices. One is file system based, and the other is block device based. Choosing a proper type of image is fundamental to the solution because it influences a lot of things. So my choice is block. And here is my thoughts. A file system-based remote image provides a file system interface directly to containers. It is a natural extension of container image, so it incurs less mental friction. A block device-based remote image usually works together with a regular file system such as ext4 so as to meet the user's needs of files. And the block device can be easily integrated with not only containers, but also virtualized secure containers and virtual machines. So technically speaking, block is more universal. A file system-based remote image is more complex, as the file system interface involves many operations that have complex semantics. So it is more difficult to get stable, more difficult to apply optimizations, and more difficult to develop advanced features, such as extended attribute or cross-layer data reference. And it is not universal. It doesn't allow users to choose their best fit file system, such as ext4, NTFS. On the other hand, a block device-based remote image is much more universal because it allows the users to choose the best fit file system. For example, a Windows container running on a Linux host may want to choose NTFS as its image file system. A block image has smaller attack surface, so it is easier to get secured. In fact, block images have been extensively used for decades, and their security is well known. According to this analysis, we base DADI image service on block device. Although we are working almost alone, we believe this is the best approach for container system. Here's a brief background about the layer structure of container images. Container images consist of multiple layers, and each layer is a change set compared to the merged view of previous layers. Each layer is the files added, modified, and deleted, and the layers are shared by multiple images. Each container also has a container layer. It is a change set compared to the image. Usually, the layers are stored in separate directories, and a merged view is created with a kernel module called overlay.fs. DADI remote image consists of three components, and the first is a layered image format called overlay block device. It is based on virtual block device and works together with a regular file system such as ext4 or NTFS. The second is the online decompression format. It is seekable and supports online decompression. And the third is a P2P on-demand read with a tree structure topology to cope with the scalability problem. Each layer in DADI is a change set of overwritten data blocks. There is no concept of files or file system, and we have an index for fast reading. The index has variable length entries to save memory. Each entry leads to a chunk of data within the image block. Logically, adjacent entries are combined to save memory. And the index is an array of non-overlapping entries sorted by their logical offsets. When reading the image, we perform a single read query over the index instead of block-by-block queries. The indexes of multiple layers can be merged in advance so that a single query can handle any number of layers, and the performance doesn't degrade with the number of layers increasing. This is a key advantage over OLFS. We analyzed our production images and found that the number of entries in a merged view is less than 4,500, which consumes only 72 kilobytes of memory. We believe memory footprint is important because containers are often used for high-density deployment. To study the performance of binary search as the range query algorithm, we performed the micro benchmark on the index. The result is shown in the figure. A single CPU core can yield over 6 million QPS for our production images. I believe it is acceptable for an image service. DADI implements two kinds of readable layer. One is a log structure based, and the other is based on a sparse file, which is suitable for local storage. We maintain a separate index with red-black tree for efficient insertion and deletion. When building new layers, DADI commits only useful data to the read-only blob, eliminating the garbages. At the same time, DADI also sort the data blocks by their logical offsets so that adjacent index entries can be combined together as a single one. DADI's Z file is a seekable compression format that supports random reading. Z file achieves this with block-by-block compression schema, so that when reading some content, Z file can decompress only involved blocks. By the way, Z file can encode any file. It is not tied to DADI image. We have a P2P transport with a tree structure topology, which is maintained by the root node. And a separate tree is constructed for every image blob. Every node that participates P2P transferring caches recently read data blocks, so that they have data to serve other nodes. When the node needs to read data, it simply sends a request to its parent node, and the request is likely to hit the parent's cache. In case of cache miss, the parent will forward the request upward recursively until it is fulfilled. This is the whole I/O path within a host. Read requests from applications are first sent to a regular file system of the image, and then to the virtual block device created by DADI image services, and then forwarded to overlay BD and Z file in our user space daemon. Local layers will be read from a host file system, and the new layers will be read from remote nodes via P2P subsystem. This is the I/O path for virtualized environment. It is similar to the previous one with DADI integrated to hypervisor as a block driver. And evaluations. The left figure shows the result of code startup of a single container of WordPress. We can see that DADI is much faster than other approaches, no matter starting from registry or P2P root. In case of warm startup, as shown in the right figure, DADI is still faster, especially when disk performance is limited. The left figure shows the result of startup latencies with trace-based prefetching. We can see that prefetching dramatically increases startup performance, and the result is getting very close to that of warm startup. The right figure shows the results of batch startup of multiple containers. Note that the startup latency with pseudo's slacker begins at 1.5 seconds for one instance and increases to 2.3 for 32 instances. On the other hand, the startup time with DADI remains largely constant at 0.7 seconds as the number of instances increases. To study the scalability of DADI, we have specifically created an application in Python called Agility, and we start 10,000 instances of Agility on 1,000 hosts. The results is shown in the left figure. We can see that cold startup latencies are very close to that of warm startup. The right figure shows the projected latency of hyperscale startup. In this setup, we evaluated only a single branch of the P2P tree. We compared 4 different kinds of trees. The results indicate that the binary tree performs a little bit worse, and others performs similarly better. We evaluated I/O performance with DU and TAR, comparing against overlay FS and LVM. The results show that DADI's I/O performance is better than both of them on both SSD and cloud disk. DADI is open source software and has become part of Containerd. We have quite a few contributors, and some of them, among others, are worth mentioning here. The first is Shiwei Zhang. He's from Microsoft. And the second is Fu Wei. He's the maintainer of Containerd. And the third is Haibin Huang. He's from Intel. We are also contributing our P2P subsystem to Harbor as an extension for massive distribution of images. And we are developing a Linux kernel module to attach DADI images files based on the device mapper framework. We will also contribute it to the Linux upstream once when it is ready. Okay, thanks.